My name is Ian Kollipara. I am currently a senior standing at Concordia University in Nebraska. I am in elementary education and computer science double major. If you want to get a hold of me, that's my email. And if you want to see code I've written outside of this project, that's my GitHub. So my topic for this summer REU was modeling safe and reliable cyber physical systems using timed Rebecca. So a few terms I want to define before I get into the rest of the presentation so you're a little more informed. Formal verification when it comes to programming, you can kind of think of formally proving something in math. It's making something an explicit property of that program in the sense that something is an explicit property of something in math. And then cyber physical systems are just an integrated part of integrate both physical and cyber or electronic parts. And specifically, NIST has a few definitions it provides. I'm working with the definition that it is a subset of Internet of Things, such so that although networking is considered, it's not necessarily my primary concern when I'm talking about cyber physical systems. So on to the main issue at hand. In the this quote says the major challenge to ensure and to develop the security, safety, and reliability of cyber physical medical devices, since such systems have become increasingly interconnected and complex. So as systems advance, they become more complex, and our needs for them become more complex. However, in safety critical industries such as the medical industry, the need for safety rises just as much as that increased complexity. However, the needs to meet that and maintain that needed safety aren't always there. This is especially noticeable in systems that have ad hoc modeling and ad hoc thought processes when it comes to connecting other devices. And as such, there's been a growing trend towards model-driven design in these areas. So there are a few current solutions in the space that address modeling, especially in the medical field. The first one is Simulate State Flow. This uses a visual programming language as opposed to something more code looking. It has no mechanism in particular for temporal logic. I'll explain what that means later on, but to suffice it to say, it doesn't have mechanisms to test things over the course of a runtime, like over the course of time. And it's based on CORE's communicating sequential processes, which is an alternative model of computation. It's much more complicated than the model I'm using for concurrency and to talk about, which I'll get to later. The other one is a solution proposed that uses the same technology I'm using. However, the technology is geared towards a more iterative way and draws more from behavioral programming. Mine is more integrated to work with heavily regulated industries and focusing more on a waterfall style. It also uses a different hazard analysis technique. So my proposed solution is built on three main components: timed Rebecca, STPA, and LTL. So the first, I want to set the baseline, the theoretical baseline, which is the actor model of concurrent computation. This was created by Carl Hewitt in the 70s to deal with rising complexity back then. It basically encapsulates everything into an actor. An actor is the fundamental unit of computation. It has three defined actions that it can do. They communicate explicitly through message passing. And in particular, the semantics allow for unbounded non-determinism, which means it will always service a client. In bounded non-determinism, which is what CSP does, it means this program can always make the choice to not service a client. That's not possible in the actor model. And the reason I chose the actor model as opposed to CSP is that the actor model is fundamentally far simpler to conceptualize than CSP. And the language is much simpler, which I think is really important when you're just trying to do modeling. You need to have people be able to understand the modeling language and the theory behind it quite easily. So that's one big reason I chose that. Now, the language timed Rebecca debuted in 2005 as an actor-based modeling language. Its syntax is a C-style syntax using curly braces, types before the name of the program, semicolons, the whole shebang. And it supports LTL as formal verification, which we talked about a little bit. In particular, it's seen use, Rebecca as a whole has seen usage in other safety critical applications like automobiles. There's a great paper talking about an extension on Rebecca guided explicitly at automobiles. And the time Rebecca, this specific extension introduces syntax and language that allows for dealing with network delays and other hard time requirements, which is really important in a safety critical application. So here's an example of it. That everything is defined as a reactive class. The name of the class is next. That 10 is the amount of space in its message queue, the message mailbox that it'll process. Known regex are the other things that can communicate to. State vars are just internal state variables. The agent with no prefix is the initial class, is kind of like, you can think of that as the constructor. And then message serve, and then the rest of that, that's basically a method definition. Message servers act as the method definition. So on to the last part, the next part, which is linear temporal logic. LTL is a formalism, it's a logical way of expressing statements about time. In particular, it's used to formally verify time for Rebecca, which is why I think it's important to explain. There's a bunch of new operators. In my opinion, for what I've seen, the most important ones to note are F and G. F is eventually, which is eventually the right-hand side of F is true at some point during the execution from the current point. And then with G, the right-hand side of G is always true at every single point from the current point. So that idea of current point and not necessarily start is due to the way temporal logic works. You're moving along time. So something that may not be true at this point in time might be true in the next point in time and whatnot. And that unit can be defined based on the application. So the last part is the hazard analysis aspect. System Theoretic Process Analysis, or STPA, was introduced by Leveson and Antone in 2013 in his Antone's thesis he did under Leveson. It builds on systems theory over reliability theory. Reliability theory is the theory behind FEMA, FTA, and a bunch of the traditional hazard analysis techniques. It's concerned more with control. And in STPA, loss of control is what really defines a hazard. And because of that, hazards are much more defined in terms of their loss and also in terms of how do different components interact. And it has been shown in a few case studies that, well, quite a few case studies actually, that hazard analysis done with STPA finds more integration and component-to-component communication faults. And it's those that I think are unique, that makes this uniquely suited to work with Time Rebecca, because you're looking at these interlocking actors, these actors that are communicating and have interlocking control loops. And so STPA provides that great hazard analysis that's uniquely suited to deal with interlocking control loops. So I wanted to provide in particular though, STPA generates these unsafe control actions and constraints. And an example one is down there that's pulled directly from the STPA handbook source down there. And these are basically the final results. This is what you end up with. You end up with these statements. And they have a pretty set in stone syntax, of which I've kind of given a little bit of a syntax definition up here. And this is the key part, because the technique is by converting those previous statements into LTL expressions, we can formally verify safety requirements as properties of the model. Then through this, the models are the safest model to develop from, because these safety requirements are no longer things that the software has to abide by, like outright. The model itself has these as properties. The model itself is safe. And in particular, Time Rebecca supports code generation. And so you're able to generate code from this model that already has these safety properties as intrinsic aspects of it. So the technique comes down to 3 steps. Identify the component parts of the UCA statement, identify the state to observe, and then build the resulting expression. So I want to talk about my hypothetical case study, which was an insulin pump. The scenario is there's an insulin pump being designed. It must always be connected to a wireless controller that's like the monitor. And these 2 devices communicate over an unspecified protocol and receive message. And the device in particular receives messages on device failure. The device is being developed in regards to the process outlined in the STPA handbook. And there are 2 primary components, the insulin pump controller and the wireless controller. So The first statement I want to look at is the wireless controller must provide update insulin info command within a certain amount of time units to the insulin pump controller. So first is identifying the component parts. Those are the wireless pump controller and insulin pump controller. These are often the big proper nouns and usually correspond to the defined reactive classes in Rebecca. Next, we want to identify the state to observe. This is important because just like in a lot of object-oriented programming, you can't necessarily observe a message being sent or a method being called, but you can observe the results of it. You can look at, oh, is this internal state modified? And so, although I cannot look at the update insulin info command, I can't force it to be shown to me. I can't observe that it's being sent. I can observe if these two are in sync. And if these two are in sync, the message must have been sent. Now, how do I address the real-time component? This one is part of the benefit of Time Rebecca. We can modify the model code to include the syntax of deadline. Deadline basically says if the message is not acted and processed within this certain amount of time, it's invalid. And when it's invalid, that means it can't be processed. It doesn't matter. And if that happens, that would violate the constraint and it would force the model would have to abide by it. So from here, we can construct our LTL expression, which is taking two different things. I did a little bit of research into insulin pumps just to get a baseline idea of what I was talking about. Basal rate is the common rate of insulin that's applied. And then glucose level is just obviously the amount of blood sugar in your blood. Sorry. And so what we're saying here is eventually these two are in sync. And the reason we use eventually rather than globally is that it may not start in sync, but it will be in sync at a certain point of time in the execution. And we know this has to happen within that set amount of time due to the adjustment we made in the model. So I want to give a second example that kind of also touches a little bit on networking. Insulin pump must provide alert command when wireless controller is down. So again, let's follow the process. We identify the component parts, insulin pump, wireless controller. Second, we identify the state to observe. In this case, it's the wireless controller status and is the insulin pump beeping or alerting. I chose beeping as the alert mechanism. So the reason we have to observe the status of if it's up or down is that due to the semantics of unbounded non-determinism, it does pose a little bit of an issue in is a system up or down. However, being that this is a safety critical application, I would be okay to assume that these devices are in constant communication. And if one is failing, it will send out a message. And the other one can, in its own implementation, provide mechanisms to address checking if it's alive or not. This is simply just an example for here. So from here, we can generate our LTL expression, which is globally, whenever the wireless controller is down, it would imply that the other device is beeping. And imply is borrowed from first order logic, all the stuff you see when you do like discrete structures or all other things like that when you get into that part of computer science math. But suffice it to say, it's basically saying whenever this is down, this device is beeping. And if it's not down, it doesn't matter. But if it's down, it must be beeping. And that's true for the entire execution lifetime of the program. So the technique right now is a little more procedural than mapping. And I'd like to get to mapping. I think a mapping is much more secure. It also provides a really straightforward way. And in general, I think it's the preferred mechanism for doing this. One issue that was brought up in a paper called On the Use of STPA is that STPA can be a little unfamiliar. It's quite a new technique. It's only debuted in the last 10 years. And so, although I think it's an incredibly powerful hazard analysis technique, and I think it's incredibly suited for safety critical applications, especially this specific realm of safety critical applications, it's still unfamiliar. And so that is a certain issue with the technique. And I would also like to move from a technique to a methodology that incorporates some of the aspects of the STPA handbook's development process so that there's a much more guided way for developing these safety critical applications. Future work is to actually test this. I don't have the resources nor the personnel to do a medical case test study. So the hypothetical is one I thought through and talked through, but I don't have any true way of testing it. Again, moving from technique to full-blown methodology, I would also like in the future to potentially generalize it from just the medical field to maybe other heavily regulated safety critical applications. And this approach right now is very theoretical, and I'd like to move more into that implementation realm. Here are my references, and thank you for your time.